Heterogeneous catalyst. Heterogeneous catalyst has a different state as its reactant. So in this example, we're using nickel to catalyze the Haber process. So in order for transition metals and their compounds to act as good heterogeneous catalysts, it is primarily due to the availability of their partially filled 3D orbitals. These 3D orbitals could then be used to form temporary bonds with reactant molecules, and this is how the reactant molecules are able to be adsorbed on the catalyst surface. It's important to take note that the adsorb is AD, not AB. By holding the reactants close together on the metal surface in the correct orientation for chemical reactions, covalent bonds are in fact weakened. So activation energy is reduced and the reaction pathway has changed, so reactions can take place faster between the reactant molecules. Desorption occurs after the product molecule is formed and leaves the catalytic surface. The catalytic surface could then adsorb another new batch of reactant molecules. And that's how heterogeneous molecules work. In the case of homogeneous molecules, transition metal and their compounds are deploying their ability to exist in various oxidation states so that they can play both the oxidizing and reducing agent. Let's take a look at a specific example. In this catalytic reaction between peroxide disulfate and iodide reaction, we are using Fe2+ or Fe3+. First, the activation energy between S2O2- and I- are extremely high, since both are negatively charged and they electrostatically repel each other. So with the use of Fe3+, for example, which can reduce to form 2+, and Fe2+ can then be also oxidized back to 3+. So with that, let's list down all the standard electrode potential value that we can take from the data booklet. So bear in mind that we have peroxide disulfide as the reactant and iodide as the other reactant. And we are starting off with Fe3+ as the catalyst. So in this case, by looking at the standard electrode potential value, Fe3+, which is the left-hand species, is now an oxidizing agent, and it will be able to oxidize iodide to form iodine. Since the electrode potential of Fe3+ is 0.77, and in the case of iodide is 0.54. And during this redox reaction, Fe2+ is produced. And with the production of Fe2+, now peroxide disulfate can now behave as an oxidizing agent to oxidize Fe2+ to regenerate your Fe3+. And in this case, the standard cell potential will be 2.01 volt minus 0.77, which will also be greater than your 0 volt. And that is how a transition metal like Fe3+ operates as a homogeneous catalyst. Of course, using the same concept, we can use Fe2+ instead as a catalyst. If Fe2+ is used instead as a catalyst, then what happens is that it will actually reduce your disulfate. And in the process of reducing disulfate, it will produce Fe3+, which can then oxidize your iodide to form iodine. And in that process, Fe3+ will be converted to 2+, which means your Fe2+ as a catalyst is being regenerated.